right, here we go. We're going to take a look at Jeffrey Bezos right now, and a pretty cool problem here. And we're going to need Desmos in this section. We're going to do a lot in Desmos. In fact, pretty much the whole thing in Desmos. So this is a great problem. Let's take a look at the net worth of how much money Jeff Bezos was worth when he started in 1994 versus kind of where he is in 2026. You can see that, okay, he was making a couple billions, went down a little bit, bummer, and went back up. So a lot changed beside his hairline there over the years. His money changed too. I graphed it for you, so you're welcome. There it is on your paper for you. You've got this nice curve that he went up, he went back down, and back up again. So what we're going to do is called regression. So we're going to find the best fit curve that goes through this. And just like we were doing last section where you had to identify, is it quadratic, is it linear, blah, blah, blah. We're going to tell you this time, so that's kind of nice. We're going to say, hey, you must use this function. So when you look at this function, you see the highest power is 3, so I'm going to use a cubic function. And I know it's a cubic function, and the other interesting point here is that the function is over time, but time is the number of years since 1994. So a lot of times with time, that's a lot of time, when we say t, we're talking about t, we like to say this is 0. It just helps because if there's any rounding, you've got these big numbers for x or for your t, it's kind of rough. So if we call him times 0, then 4 years later is 1998. And then 4 years after that is 2002, or 8 years after 1994. So we can kind of fill these in. That's 14. Jot these down. You're going to want these numbers. 7 years later is 21. So 2015 is 21 years after 1994. Awesome. So let's fill these in. We got 24 is 2018, 26. And then the last one looks like it's 32 here. So that's going to be our x's, our time, our t in this case. And this is going to be the net worth over time. Awesome. So let's get over to Desmos and let's go ahead and make that graph. So I gave you the graph already so you would have it. That is not Desmos. Let's try that again. Desmos. There he is. Okay. So if I want to make a table in Desmos, you just come over here and you're going to add, instead of an expression, you're going to add a table. We're going to type this in. Okay, so we're going to fill in for x, we're going to fill in our time, and t, so it was 0 is 1994. He had no billions dollars. Bummer. 4 years later, he's at $12 billion. That's pretty epic. So let's just go ahead and fill these bad boys in here. We've got 14 years. That was his roughest year, only $2 billion. Still a pretty good year, man. Still pretty good to be worth $2 billion, I'd say. We got 24 is $100 billion. And 26 is 136 billion. Last one here. 32 years later, $256 billion. Oh my gosh, that's a lot of money. So check it out. Here's the graph over here. Not real exciting because I'm only looking at the origin here and within 10. So check it out. If you click on this magnifying glass over here where it says zoom fit, boom, it's going to automatically kind of highlight that data. You also can come over here to settings and set your own X and Y window if you want to look at it yourself. But when it's data, I'm definitely going to hit that zoom fit. So now I can see that's the same picture I put on your graph paper for you. So what am I going to do? Come up here to this little thing. So this is the best fit line or the best fit curve. It's called a regression. So we're going to hit this. It defaults to linear regression, but does this data look linear? No, it's not linear. And we went ahead and told you it is cubic, so here's your list of things to choose from. We got a bunch. We're going to do a cubic regression, and there it is right there. That is the actual equation right there. Here's what's cool about that. If you hit it right above it, you can pop it out, and it actually go ahead and throws it into your as a function below here. So you can use it as a function here below. Awesome. So there's our equation. So we have to do A, B, and C. Let me snag this real quick. All right, so I went ahead and put the graph over here so you can see the best fit curve, that cubic function going in there. So again, this is a model. I'm not going to hit every single point perfectly. It tries to get the closest curve that's, equal points above, equal points below. Does this fancy thing with residuals. But we're trying to figure out, hey, what is the best fit model? So for a cubic model, this is a great fit here. I went ahead and copied it over here. Let me make that a little bit bigger so you can see that. Whoopsh. There it is the function. So when it asks you these things, it's just going to ask you for the coefficients. So it's going to ask you for, hey, what's the A term, B term, C term, and D term. So you can see them right there. Let's go ahead. When we write these, we're just going to say A equals. Remember, the rule is 3 decimal places. I do 3 decimal places, and I just stop writing. I think that's the easiest. It's called truncating. You just don't have to worry about anything. 1, 3, 2. I'm going to stop writing. Boom. Part C is right here, 0.057. And the last one, part D, is 5.9. Oh, I almost got that one wrong. I can't even copy the answer. It's right there in front of me. 5.597. 3 decimals, stop writing. Now, could you round this? Sure. The rounded version of the first one, you could round up A. If you like the rounded version better, you could do 0.012. Totally down with that. If you really dig the rounded values, they also count. So sometimes I'll write both answers, but usually in the practice solutions, I just default to the truncated one where I just sit there and just stop writing. Just a little bit easier for me. I'll give you the rounded values because, that one rounds up. Dang it, see that extra work. Round that one up to 0.58. I think these all rounded up, didn't they? So the ones in blue, I need closure now. So, oh, there it is. These are the rounded values. Either one are acceptable, but I'm going to do truncated, just so you know. Awesome. So we have the function here. That's going to model it. Why do we have a model? Well, we use the model to make predictions. So we want to know what's the average rate of change according to my model, according to the function, according to the n of t. What is going on from here to here? So I know I have the real point at 2008, but I want to use the model's point at 2008. So about 14. So I can see there's where the real one is, but see how my model's a little bit different here. So we're going to use the model from 2008. What I say to it? 2022. And we're going to say, what's the average rate of change? 2022, which is, what, about 28? Is that what we're going to say? 28. So it's going to be somewhere out here-ish. And we're going to find the average rate of change, or we're going to find the slope of this line. So what is the average rate of change between those 2 points? So we said 2008 was when t equals 14. And this was, I already forgot it. Man, I got some short-term memory. 28. It's not on my table, but I was using my table to help me find it. So t equals 28 would be 2022. So really, this is great. Once we have it, we can just do plug and chug. We're just going to find the slope of the line. So we're going to say, it doesn't matter. A lot of people like to do 28 minus 14, the big one minus the small one. I don't really care. Here's the notation for it. It's y's over x's. Remember, you're just finding the slope of the line, so we're doing y's over x's. But I like that fancy notation. We got to use the real notation here. But really, this is just slope, y minus y over x minus x. And we did rate of change earlier in chapter 1, so we should be good. So here's the thing about this. I got to use my function here, so I got to go back to Desmos. Let's hope I can find it faster. There it is. Boom. And I'm going to find these points. So now these are pretty hefty decimals here. We don't like to round until the very last step if we can. So we're trying not to round. So here's a little trick for you. If you want to know what is the f of 14, you just type in the f of 14. Oh, that didn't work. Why didn't it work? Let's change this over. So it's a y equals, but we can change it to the f of x. So now when I call that instead of y, the f of x, or you could use whatever letter you wanted, I can see my y values that. That's pretty cool. Love me some Desmos. Hook it up. We said this one was what? We want to know when it's 28. All right, so I just want to make sure we know what these points mean. So when you plug in 14, 12.958 comes out. That means 14 years after 1994, Bezos is worth $12.958 billion. So again, be careful because the table is going to tell you, sure, he was only worth 2, but according to our model's overestimating here. It's a little high here, well, a little high, just a couple $1 billion. But you can see it down here at 2. It's the real life data was 2, but according to our model, we would have been off here by about $11 billion, just $11 billion. And same thing for 28. That's 28 years after 1994. He's worth $163 billion. So there's a difference between the actual point and the predicted values in these bad boys here. Just want to make sure you're cool on that. So I can subtract these y values, boom, and get my rate of change. Or, check this out. This is even better, man. Let's go ahead and make him the fraction. What do we say, 28? 28 minus 14. I know a lot of people like to put the big number first. And then this was the f of 28. Basically, Desmos does all the work for you. Check it out right there. So there's the slope of the line. What's nice about this, there's no rounding. I don't have to worry about did I round too early because you don't want to round to the very last step. So there it is. Let me snag this here for awesome. There it is right there. And again, if I was writing this as a answer for like a free response or whatever, I would go ahead and just stop writing. Just truncate that bad boy, because look at this. You round that one up. Now you do more rounding. You got to round your round, all that stuff. So back to a little rate of change. We're going to use predictions from the model. Remember, the model predicts. Just be careful. We only like to make predictions inside of our data set. So we don't know what's going to happen in the future, so we try to make our predictions between 0 and 32 in our data set. If not, we're extrapolating the data. But that's regression. Fantastic. All right, so what types of regression are we going to do? Well, the top row here is our polynomials. So the top row is polynomials. That's what we're doing in Chapter 1, polynomials. So you're going to see these bad boys. So if you see data like this, like in a line, you're going to use the linear one. There you go. But what's nice about this, honestly, it's going to tell you what to do. So it's going to say, do a quadratic. I want a parabola. How are you going to know? Well, you're going to see x squared in the equation. So this would just be something with x. If your highest power is x cubed, you're going to see data that looks kind of like an n. If it's quartic, fourth power, and that's going to give you a w or an m, maybe like a McDonald's or something. I flipped it just so because it could be negative. But they're going to tell you this is the highest power or the degree. They're going to tell you which one to use. Coming up, though, just so you know, don't freak out. There are more. You know, we're going to look at exponentials. Remember, oh my gosh, that was a rough one. Remember exponential growth? Grows really big like that. And logarithmics, the inverse of that. That's coming up in Chapter 2. Get excited. We're almost in Chapter 2. There is another one on there, logistics. I don't know if you've seen this one before, but it's usually like populations start off at a level. They increase to like a maximum threshold, like how many deer are in a forest or something. They look like that. And then Chapter 3, we don't really do too much of those. We're going to get into sine and cosine. Remember these like sound waves? Womp, womp, womp. I love these right here. These are so fun. They're on there. There's also another one called a power regression, but don't worry about that one because it's just any power. Your powers can be decimals. But for us, I just thought, just in case you're questioning all those, we have just the polynomials. Look for what degree it is, and then that's the one to pick, and then it gives you the equation. Awesome.
Let's talk about the other kind of word problem in this section that can happen is things that are inversely proportional. Now, these are actually pretty chill, but they can look kind of crazy. Just know the formula for inversely proportional is just y is some constant over x. So don't freak out, where k is just the constant of proportionality. So if you have this formula, it's really pretty chill. Don't freak out. Sometimes these get super sciencey, but I mean, I like science, but I'm not a Stephen Hawking here. So don't freak out. You can still do it, even if you don't know exactly what's going on in science. Just listen, just follow the wording here. So, example, the force in newtons exerted by a magnet of metal object is, here's the key. As soon as you see inversely proportional, we're thinking this formula right here. So, and then write what you know. You have a force. The magnets have some kind of force, so I'll call it F. I know it's going to be K over something because that's what the inversely proportional means. It says the square of the distance. I can square a distance. So again, don't freak out. Just kind of set it up with some letters. Then we're going to plug stuff in. So it tells me, hey, your magnet has a force of 60 newtons, so just plug that in, 60 newtons right there. I don't know what the constant is. You don't know what K is to start these usually. And then it says it's 60 newtons on an object if it's 2 centimeters away, so that's going to be 2 squared right there. And then we just got to solve for this, so don't freak out. We're actually going to find K, so that's really just 4. I'll write it. Oh my gosh, that 60 is terrible. I was trying to go too fast there. So it's K over 2 squared is just 4. And now let's solve this bad boy here. You're just going to times both sides by 4. So not bad. So really we're looking at 240 is our K, or our constant of proportionality. So once you have K, you're golden. Ooh, that's a rough looking K. Is that better? Just make it bigger and then it's okay. Okay. So I'm going to come over here now that I found it, and I'm going to use it. So I know the equation was force equals K. Well, I know K is 240. In this situation, I just found K, and it's over the distance squared. So there's usually a follow-up question here. They kind of give you some information. They say, okay, well, what about when the force is 10 newtons? So put that in for 10, and then I've got 240 over d squared, and then I'm just going to solve for d squared. So the key is just kind of set it up, and then it's just a matter of plug and chug, man. Just kind of power through it. Let's multiply both sides by d squared. Multiply by d squared. These cancel. And then I've got 10d squared equals 240. And then I'm going to divide by 10. My handwriting is going downhill here. So those are gone. So we're looking at what? So d squared is 240. Oh, I'm sorry, it's 24. Oh, big difference there. So if I want to find D, just square root both sides. It looks like the square root of 24. You can go ahead and decimalify that if you want. It's somewhere almost 5, like 4.8 something. Or leave it as the exact value. We should probably label it though. What is this? We're talking about, it must be the square root of 24 centimeters away. Boom, that's it. So you don't have to know a ton about magnets. You just got to set up and know this little y equals k over x. So there's a couple problems on inversely proportional. Nice. All right, let's wrap it up here with some piecewise functions. So we kind of did this last section. When we were looking at the graphs of piecewise functions. Now we're going to look at them algebraically. We're going to actually look at the function here and use that to solve some problems. So situation we got going on here, we've got a big snowstorm and the snow accumulating. So x is the times after the snow started. F is the depth. So I want to do something like, hey, find the f of 7. So let's break this bad boy down. What's going on over here? So check it out. This function represents what? 0 to 4. This is the first 4 hours of the snowstorm. So in the beginning, it's a quadratic, which means it's probably snowing pretty quickly, coming down pretty good. Down here, this is for hours 4 through 6 after it started. What happened here? Nothing. It quit snowing, so it stayed at 12 inches of snow, didn't move, no snow going on. But then it picks up again from hour 6 to 9. I see it's not snowing as fast. It's linear, so it is kind of going on there. Awesome.
All right, so let's use this piecewise function to find the f of 7 here. So what are we going to do? So fx is 7. We're going to plug 7 in. 7 goes into this last part of the snowstorm here, this bottom part between 6 and 9. So to find the f of 7, whoosh, we're just going to plug him right in. So we're going to say, hey, replace x with 7. So it'll be 7 plus 6 is 13. Awesome. So what does that mean? How do we put that in context? I'm going to type it because my handwriting can be a little rough sometimes. So it means what? After, 7 hours? The depth is, what do we say, 13 inches. So that's how much snow we have in 7 hours. So we can make sure we have that in context. Awesome. Boom, there it is. Awesome. So now let's find the average rate of change between 4 and 5 hours. So I need to know, hey, if I put 4 in, what comes out? And then I need to know, hey, if I put 5 in, what comes out? And then I can find the average rate of change of the two. So when I'm looking for 4 hours, I'm going to scroll up to this first top part of the piecewise function, that quadratic there, because we're saying it's inclusive of 4, so we're going to put 4 in there. So this will be replace all your x's with 4. Whoosh, throw this bad boy in there like this. And let's multiply that out. 16, 1/4 of 16 is 4. Plus 8 is 12. Fantastic. Awesome. Then I'm going to say, where is it at 5 hours? It's between this. Oh, I could do this one all day long. This one's my favorite. There's no x here. It's a constant. It's always 12. So this is going to be 12. Oh, check it out. So what's going to happen here? What's the average rate of change from 4 to 5? Well, let's write it out so we can see it. If 5 makes 12, 4 makes 12. So what's going to happen? There is no rate of change. At this moment of time, there's actually no rate of change going on here. So we are getting no snow on average from 4 to 5 hours right there. Fantastic. That's it. Good luck on the master check. Peace out.